So I'll start with a bit of background. Thank you for being here. Go has been my favorite language for over a decade now. In 2014, I created Tendermint to solve the blockchain consensus and nothing at stake problem. Tendermint is a classical BFT engine written in Go, and it's used by many well-known projects today. In 2017, we launched a blockchain powered by Tendermint called Cosmos. It was the first to offer blockchain-to-blockchain interoperability through a protocol called IBC, Inter-Blockchain Communication. Along the way, we created the Cosmos SDK. It's the most popular Go framework for blockchain development even today. But I'm here today to talk about Gno and the lessons learned about Go while implementing the Gno virtual machine. Gno is a deterministic Go interpreter. It's also a transactional interpreter, and I'll show you what that means. And it's also an auto-persistent interpreter. The problem that the Gno virtual machine solves uniquely is that it enables seamless interoperability or seamless composability of untrusted user programs, written not just in Go, but any general purpose language. So that's a strong claim, so let me explain what that means. And here's what I mean by seamless interoperability. Here on the left, Alice has a program that keeps track of the number X, can be changed by anyone. And Bob has a program that increments that number in Alice's program. The semantics of the language, like importing modules and the calling of functions and type checking, at its core is about safe interoperability. So we developers make use of this interoperability every day, but it's with trusted code. Right? Libraries or packages that we package together and compile together into a single program generally. But how can we make this interoperability work between untrusted code? Code that can hang or panic or tries to do bad things? The obvious solution is to use something like protobuf gRPC between two computers or containers, something like that. One server controlled by Alice and the other by Bob. And something like protobuf can generate code that makes this almost work. But even still, this example doesn't make much sense because nothing is being saved to disk. But what if it did? Why doesn't it? How can we make these two programs just work the way we want? Let's go even further. On the left, Alice has a program that represents a forum. And on the right, Bob is registering a callback function to thank every commenter on his post. Tools like gRPC, they pass parameters that are simple messages of structured data, but they don't allow the passing of more dynamic data like closures or callback functions. And again, even if they did, it would be more complex, and you'd have to deal with network failures. And there's still the issue that you have to persist the data to disk. So how can we make this example just work? Now, what I'm going to say is going to trigger some people because it involves an industry that's extremely divisive. I'm talking about smart contracts and blockchains. Because the closest thing we have to making those examples work are smart contracts. But don't worry, this talk has something for everyone, so hear me out. Smart contracts are all about untrusted code, making untrusted code interoperate. And it's just that the state of smart contract platforms today is immature, kind of like what programming languages were back in the 50s with Fortran and COBOL. Today, Solidity is the most widely used smart contract programming language. It was also the first. Even Rust is used for smart contract programming, Haskell and C++. You don't see Go here at all because while Go is a popular programming language, even for building blockchains and smart contract platforms, Go itself is not used as a smart contract programming language. And Solidity has a lot of limitations, partially because it's a new language, but primarily because of the limitations of the EVM. Solidity has no garbage collector. Every function is limited to 16 variables. It doesn't support closure functions, and you can't even declare self-referential recursive structures to create like linked lists or trees. So why is Rust, C, C++, Haskell, why are they not more popular than Solidity? Okay, to illustrate, I'm going to use a popular Rust smart contract platform by Near. Near is a smart contract platform, lets you program in Rust. This is the most basic example of Rust code that calls another contract in Near. It gets compiled into WASM. And the reason why WASM is used is because WASM helps deal with untrusted code. Code that can have an infinite for loop, allocates too much memory, and so on. WASM makes it's like running Docker containers, but it's more efficient. And the problem is, this code is peppered with macros. It doesn't look idiomatic, and it's not even the worst part. You can't receive the return value of another program synchronously. You have to wait until the next block to get the result back from other WASM programs in the air. And different WASM-based smart contract platforms make different trade-offs, but they all suffer from this kind of interoperability limitation. The interoperability of WASM user programs in general is limited by the fact that they force you to use the actor model. They force you to pass messages, simple messages between programs. The frameworks try to abstract this away, but it's still complex. And in the end, there's a lot of boilerplate code that doesn't represent succinctly the logic that you actually want. And this is why we built the Gno VM. It's a virtual machine. It offers seamless language level interoperability without the complexity. It has fine-grained memory, CPU, and storage limitations, which is needed for calling untrusted code. It automatically persists values to disk after every transaction, so you don't need to worry about databases or leaky ORMs. It's deterministic by design, and the architecture of the machine and its implementation is simple and intuitive. Right now, it's less than 30,000 lines of code, and most importantly, it runs programs written in Go. The GNU virtual machine is written purely in Go, of course, and it interprets the abstract syntax tree directly. It's not a bytecode interpreter. It makes the implementation a lot more intuitive. And you can see here there are 7 stacks in the machine: the op stack, the value stack. The expressions and statements are put in the stack in the machine. The opcode stack helps the virtual machine remember what to do next. There's about 100 opcodes. Each opcode has a fixed CPU cost. There's basically a big for loop where the machine fetches the next opcode and performs a single unit of computation on the AST over and over again until the program terminates. During execution, all the updates to values and the ref counts of objects like arrays and structures are tracked. And when a user's program returns, the changes are saved to disk. So as long as it's reachable from the package's global variable, it's saved to disk. So in this example, starting from the bottom, Bob's program calls Alice's function, which calls an internal function, which in turn calls Carl's function 1, and so on. And when Carl's function 1 returns, changes to Carl's package values are saved. And when Alice's function returns, changes to Alice's package are saved, and so on. Everything happens in the same call stack, so you have the same level of interoperability at the language level, both within a program and between untrusted user programs. So going back to the previous slide, I hope you see that the silly example where Bob registers a callback on Alice's forum post here, it actually works with the Gno VM, but doesn't work anywhere else. So let's talk about Go and what we've learned about Go while implementing this virtual machine. One thing we learned is that primitive values, like integers, when they're stored in an interface variable, they're actually stored under the hood as pointers. So in this example, x only takes 8 bytes because it's an integer, and while y, before assignment, it takes 16, but when you assign the number 1, 2, 3, 4, 5 to y, it'll actually allocate a pointer to an integer. So it takes 24 bytes. And also puts more pressure on the garbage collector. So y and z here require the same amount of memory, which is unexpected. It's a little more complicated than that because Go does some optimizations, but that's generally the case. And this behavior changed in Go 1.4, by the way, so some old blog posts might not be this correct. This is why all of the values in the Gno VM are represented by a struct, not with two fields, the type and the value. They're both interfaces, but also a third field, n, to hold the primitive numeric value. And this way we can avoid storing integers in an interface field and avoid a pointer allocation. Okay, related to the previous example, the lesson learned is to avoid switching on interface values when you can just do a type switch. So in our code, the primitive types, the different types are represented by numeric value. So 2 for an int, 3 for an int 8, and so on. Because we thought these types are primitive and they don't require any struct fields for customizing the type. An integer is just an integer. And we have a few places where we switch on the value of that type, as can be seen on the right, for op-add in this case. But switching on values like this is equivalent to a chain of if-else statements, if-else equality comparisons, and comparing two interface values is surprisingly slow. In comparison, switching on types can be faster because the compiler knows ahead of time what the possible types are. So here's how the code can be improved. See the difference there on the right? So we get the best of both worlds here because we switch on the type and we don't need to allocate a pointer by storing primitive numbers in the interface field v. Another lesson we learned along the way is that scopes are sort of independent of allocations, and here's what I mean. In this example, I is declared once in the scope block for the for statement, but during runtime, every iteration of I : = 0 results in a new pointer allocation because I is passed and stored by reference. And this might be obvious to you, especially if you know about loop vars, which is something else, but it's not just about for loops. Goto statements can also create implicit loops. And even without any new block of curly braces, you can end up allocating a new pointer depending on whether you go to below or above the declaration of the variable. So for this, we have to statically analyze the usage of the variable, the name, and if it's within a loop, go to, for, or range statement, we need to check to see whether the name is used in a closure or passed as a reference, and we have to allocate a heap item rather than just storing it in the scope's block space. Another lesson we learned early on is that Go's reflection system is limited. Originally, we tried to make some seamless integration between Go and Gno values and logic, so you could run Gno code and Go code that are seamlessly integrated, but due to the limitations of Go's reflection system, this magical native Go integration is never going to be perfect, so we'll probably just remove that. So I'd like to mention two pieces of future work now. The first is about upgrading Gno code. Since Gno removes the abstraction between volatile memory and persistent disk, software upgrades are going to be trickier. Upgrading a deployed Gno program is going to be like upgrading a running Go program. Okay, so upgrading a function or a method with another function. So changing the function with the same signature type is okay, maybe, because it's like iOS's Swizzle. This is already being done. Appending new fields to a struct can be problematic. It can break old logic because of the use of reflection, obviously. But it can also break old logic that uses interface type checks because you can add a field that suddenly implements an interface. Appending methods to declared types is, likewise can break old logic that uses an interface. So the second thing I want to mention is about garbage collection. So in Gno, within a transaction, we rely on Go's garbage collector to free up memory for subsequent future transactions. But the Gno VM doesn't know exactly when memory becomes available from Go's garbage collection at runtime. So currently, while the Gno VM does limit memory allocations by wrapping all Gno value allocations and tracking the total allocated memory, the amount of memory available never decreases during the transaction. This is actually pretty easy to fix. The simple solution is once the memory allocation limit has been reached, we pause execution, and then we synchronously just recalculate, retabulate all of the memory that is reachable from the virtual machine. That's relatively easy. But the future work is the difficult part. It's garbage collecting post-transaction persistent memory. So, for example, this is not the case with a single transaction, but with 2 or more transactions together, they can end up creating a reference cycle on disk. We can't rely on Go's runtime garbage collector to clear these up because they don't reside in memory. So the current option is to simply avoid creating such cycles in your program. I mean, within a transaction, garbage collectible cycles are fine. We can handle that. But of course, and cycles are okay as long as you clean them up yourself. But we plan to implement an incremental garbage collector for persistent values on disk in the future. Another option, though, is to extend the language itself, maybe through annotation like struct tags or comment directives, or other techniques to better manage ownership rules among values to help with the overall persistent garbage collection problem. Maybe it'll end up being a little more like Rust. Who knows? So to summarize, GnoLand is a distributed, multi-user, language-based operating system. It's a state-of-the-art smart contract platform. It's the Go lovers' answer to Ethereum. And we also want GnoLand to be a repository of open-source auditable programs. Even our homepage is rendered through GNO code, and you can even see the source. So the top left is the package name, the package path, and then you see a link to the source. Every smart contract can render a page, and you can always see the source for the smart contract. All right, so this talk was short. This concludes my talk. Please join us in our work with the VM implementation, garbage collection, runtime upgrading, and language enhancements, or fork the Gno VM and make an entirely new language. It's a pretty good starting point. And yes, we are hiring. Thank you very much.